Hi everybody, today's lecture is about nuclear physics. Let's get started. So a reminder about the atomic nucleus. It's a very dense nucleus in the center surrounded by orbiting electrons. So this is a little picture here with, well, one of these is neutrons and one of these is protons. And the electrons would be super far away from this. The nucleus consists of nucleons, protons, and neutrons, just said that. And they're made of quarks, which we won't worry about here. The nucleus is positively charged. And the nuclei are held together by the strong force, which we'll talk about in a second. A reminder about isotopes. The number of protons determines the identity of an atom or electron. So the proton number determines what element we're talking about. And all atoms of the same element always have the same number of protons, but they can have differing number of neutrons. And the differing number of neutrons gives you different isotopes. Let's read this. Atoms of the same element with different numbers of neutrons. Okay, let me read that again. Isotopes. Atoms of the same element with different number of neutrons. They have identical behavior in terms of electrons and chemistry, identified by their mass number, total number of protons and neutrons in the nucleus together. So the identity of the element is given by the number of protons, and the mass number is given by the number of protons plus number of neutrons. Okay, so the atomic nucleus and the strong force. When two protons are nearby each other, the strong nuclear force is really, really important and holds them together. And the electrical force, which is repulsive, is less important. So they repel each other because they're both positively charged, but the strong force overcomes that. When the protons are separated, the electrical force is strong, and the strong nuclear force, attractive force, is weak. Okay, and so it's difficult to get protons together, but if they get together, then they stick together because of the strong nuclear force being strong here and weak here. Okay, strong force is a force in the atom that holds electrons in orbit. Note that the thing that holds electrons in orbit is the electrostatic force that holds electrons attracting to protons. The nucleus that holds nucleons together. That sounds right. So B. In the nucleus of an atom, the strong force is a relatively short-range force, long-range force, unstable force, neutralizing force. So up here, because it's strong when things are close together and really, really weak when things are far apart, it's a short-range force. Short-range force. Okay, alpha, beta, and gamma rays. Let's figure this out. So an alpha particle is positively charged helium nuclei. So that's two protons, two neutrons in one particle. So that's this picture right here. So two protons and two neutrons. Beta is negatively charged electrons or positively charged positrons. So when a beta particle leaves, typically when beta particle leaves an atom, it's going to be an electron. So it takes a charge with it and changes a neutron to a proton. And gamma rays, well, that's really, really strong electromagnetic radiation, photons. Okay. So when a nucleus emits an alpha or beta particle, it becomes a different nucleus. When a nucleus emits a gamma ray, it stays the same but with less energy. And there's relative penetrations, meaning an alpha particle doesn't go very far through materials, beta particle goes farther, and a gamma ray goes quite far through materials. Okay, beta minus emission. These are the types of decays. So a lone neutron is radioactive and spontaneously transforms to a proton and an electron. So here's a neutron, and spontaneously it will transform to a proton and an electron. And this can happen within the nucleus. Alpha emission is when, new proton formed with neutron. The electron beta particle ejected from neutron, alpha particle emitted. Okay, so electron is emitted, and then a proton is formed, which then spontaneously this new element then emits a helium atom, which is two protons and two neutrons are ejected. Okay, notice here the element gains a proton, and here it loses 2 protons. Okay, so in total, that's 1 proton lost in this example. Okay, any atom that emits an alpha particle or beta particle becomes an atom of a different element always. That sounds good. May become an atom of a different element. It's because it's losing an alpha particle, you lose 2 protons, it becomes different. For a beta particle, it converts a neutron to a proton, so it's got to be different. Becomes a different isotope of the same element. Oh no, because it's changing the proton number. Increases in mass. It's going to be decreasing in mass, probably. So A. Okay. Which of these is actually a high-speed electron? Well, alpha is a helium atom. Gamma is electromagnetic radiation. So B, beta particle. Okay, nuclear notation. So this is if we want to label what type of isotope and element we have. So X is the element. Let's see, that's right here. X is the element, so that's the identity. Z is the atomic number, the number of protons. And A is the atomic mass number, total number of protons and neutrons. So see, iron, this is the element. It's got 56 total nucleons and 26 protons. Okay. This is an interesting plot. As the atomic number goes up, the nuclear mass isn't linear. It goes up slightly. So there's slightly more neutrons needed as the atomic number goes up. Okay, nuclear reactions. This is when we convert different elements into new elements. So all nuclear reactions are governed by 4 conservation laws. That's energy, momentum, charge, and nucleon number. Each nuclear reaction equation shows reactants changing into products. Only the nuclei are shown, as well as the alpha and beta particles that are emitted. Conservation of charge means that the sum of all the z values of the reactants equals the sum of all z values of the products. So that means we can't change the amount of charge in total. Conservation of nucleon number means that the sum of all A values of the reactants is equal to the sum of all A values of the products. So if we look at these, before a reaction, all the A's have to add up, and after. Before a reaction, if you add up all the A's, that should equal all the A's added up after. And same thing with Z. Okay, so transmutation of the elements. So with alpha or beta particle emission, a different element is formed. This transmutation, which occurs in natural events and is also initiated artificially in the laboratory. Okay, so let's look at this. Uranium transmutes into thorium when an alpha particle is emitted. So here's uranium-238. So uranium-238, 92 protons. It ejects an alpha particle, and what's remaining is thorium-234. Then thorium can transmute into protactinium when a beta particle is emitted. So we have thorium-234 emits an electron. One of the neutrons is converted to a proton. So we're left with, what is this, protactinium with one more proton in the nucleus. So it went from 90 to 91, but the total mass stayed the same. Okay, and so that is a beta particle decay. Okay, atoms can transmute completely into different atoms in both nature and laboratories. So that's C. When an element ejects an alpha particle and a beta particle, the atomic number of the resulting element, while an alpha particle reduces the number of protons by 2, the beta particle emission changes a neutron into a proton. So that's -2 + 1. So it reduces it by a total of 1. Oh, so I am not correct. Let's read this. An alpha particle, a helium nucleus, has atomic number 2. Ejection of an alpha particle means a loss of 2 protons. We said that. So the atomic number of the element is lowered by 2. Wait a second. We've got alpha particle and beta particle. And we know a beta particle converts a neutron into a proton. So we lost 2 and we gained 1. So I don't think this is right. They're only talking about the alpha particle getting ejected here and nothing about the beta particle. So I think this is incorrect. Okay, when an element ejects an alpha particle and a beta particle, the atomic number of that element is, well, this sounds like the previous one. So we said goes up by, loses 2 protons, but gains 1 proton, overall reduction by 1, A. Gotta be. Okay, so this one is incorrect. And then this one is reduces by 1. Okay. An element emits 1 beta particle, and its product then emits 1 alpha particle. The atomic number of the resulting element is changed by, okay, so it emits 1 beta particle, that changes a neutron to a proton, and then emits an alpha particle. It loses 2, so it's reduced by 1. So it's very similar to the previous problems. Okay. All right, radioactivity. An isotope is said to be radioactive if it changes to something else via alpha or beta decay. An example is uranium-238 to lead-206 through a series of alpha and beta decays. It takes 4.5 billion years. 4.5 billion years is the half-life of uranium. Okay, and this is a picture here of the decay chain, I think it's called, in order to get from uranium to lead. Okay. Important thing about radioactivity is the half-life. So let's look at this graph. After this looks like the half-life of this element. We're looking at this graph here. This is the amount here of kilogram of a material with a half-life of 1,620 years. That means if we start out with 1 kilogram, after 1 half-life, we'll have half a kilogram left. And then after 2 half-lives, we'll have a quarter of a kilogram left. And then 3 half-lives, we'll have an eighth of a kilogram left. So every half-life, the amount is getting reduced by half. A certain isotope has a half-life of 10 years. This means that the amount of the isotope remaining at the end of 10 years will be, we said, half. So half-life is 10 years. 10 years have elapsed. Half is left. Okay, there's radiation detectors. A Geiger counter detects incoming radiation by short pulse of current triggered when radiation ionizes gas in the tube. That's the clicky sounds. Scintillation counter indicates incoming radiation by flashes of light produced when charged particles or gamma rays pass through the counter. Okay, so this is a second way to measure radiation. Okay, carbon-14 here is, there's a lot of words here. Let's look at this. So carbon-14, nitrogen-14 is in the atmosphere, gets hit by a neutron coming from space. That converts the nitrogen to carbon-14 and a proton. Okay, and then that carbon-14 decays back into nitrogen-14. But it takes some amount of time to do that. I think the half-life is, well, not sure. It doesn't say what the half-life is. It's about 5,000 years. So we can use this to measure the age of decaying organic matter like a human body, as long as it hasn't been there for too long. We can measure the carbon-12 to carbon-14 ratio. The half-life of carbon-14 is about 5,730 years. There we go. Which means that the present amount in animal bones will reduce to 0. Well, when the animal dies, no, it'll keep decaying after the animal dies. In about 1 half-life, it'll be about half. In twice a half-life, it'll be a quarter. So it actually never gets to 0. If we look at this graph here, it never actually gets to 0. Now, in reality, eventually it'll get to 0 in a super, super long time. But for all intents and purposes, it doesn't get to 0. So it's none of the above. Okay. Nuclear fission is when we split the atom. So here we let's look at this down here. This is the important part. Neutron comes in, converts uranium-235, splits it into krypton 91 and barium-142 plus 3 neutrons. So we split the atom. Okay, and this releases a huge amount of energy because the mass of the uranium atom is greater than these 2 atoms together. Okay, and we use this in nuclear fission reactors. So this is a fission reaction. And 20% of the United States energy, electrical energy. In France, it's more like 75%. And reactors are simply furnaces that boil water to operate steam-driven generators. So it's a fancy way of boiling water. It's clean, the elimination of carbon dioxide and all kinds of pollution in the air. It's high efficiency. Drawbacks are release of nuclear waste, or difficulties with nuclear waste disposal, and the risk of release of nuclear isotopes into the air and water. Okay, here's a picture of a nuclear reactor. And essentially here's the reactor that just boils water, which then can be used to run a turbine, which then generates electricity and is sent to the grid. Okay, when a uranium nucleus undergoes fission, the energy released is primarily in the form of, well, we just have to look this up. Is it gamma radiation? Is it kinetic energy of the fission fragments? Is it kinetic energy of the ejected neutrons? It's going to be C. Okay. Nuclear fusion. Nuclear fusion is the opposite of nuclear fission, fusing nuclei together. So before, we're splitting it, when a neutron comes in, splits uranium-235. Here, we're going to take two hydrogen atoms and fuse them together to form helium-3 and a neutron and plus a bunch of energy. And then those subsequently hydrogen plus hydrogen-3 will fuse to form a normal helium atom plus a bunch of energy. Okay, when a fusion reaction converts a pair of hydrogen isotopes to an alpha particle and a neutron, most of the energy is released in the form of gamma radiation, kinetic energy of the alpha particle, kinetic energy of the neutron. Well, we just have to look this up. It's going to be C, kinetic energy of the neutron. In either a fission event or a fusion event, the quantity that remains unchanged is energy changes. Energy leaves the atoms. The mass of the nucleons goes down a little bit in a fusion event or a fission event. The mass reduction is what causes lots of energy to be released. So C, the number of nucleons doesn't change. Okay, mass per nucleon. This is telling us which is the most stable atom or stable nucleus in the universe. And it's actually iron is the most stable. Anything above iron can be broken up or done a fusion reaction done to bring it closer to iron, which releases energy. And anything lighter than iron can be fused to reduce its energy to get closer to iron. So iron is actually the most stable nucleus. I don't know why. And this is explaining that anything heavier than iron can be fissioned to create iron, and then anything lighter than iron can be fused to form iron at a lower mass. Okay, so this is showing us the mass changes. Uranium has a heavier mass than its constituents when it's broken up, and helium is lighter than 4 hydrogen atoms, or in this case protons. Okay, let's do some more questions. A sample of radioactive material is usually a little warmer than its surroundings because it efficiently absorbs and releases energy from sunlight. I'm not sure that has to do with color and other absorption things. Its atoms are continuously being struck by alpha and beta particles. That sounds good. It is radioactive. B is the better answer here. It emits energetic particles. Also true. These two are true, but this is the better answer. Okay. Which of these is the most penetrating in common materials? Alpha, beta, gamma. We just have to look this up, and it's gamma. The benefits of properly using radioactivity include measuring the proper amount of fertilizer on farms, tracing medicines in the body, irradiating food to kill harmful microorganisms. All of these. It sounds like all of these. Most of the radiation in Earth's biosphere is the result of military activities, originates from nuclear power plants, occurs as natural background radiation, is due to human negligence. We got to look this one up again. It occurs as natural background radiation. In the nucleus of an atom, the strong force is relatively, we said, short range. Uranium-235, uranium-238, and uranium-239 are different. Well, the same element, ions, that's a different thing. Different isotopes, that's right, different isotopes. Which of these is not a nucleon? Proton, neutron, electron. It's electron. The half-life of carbon-14 is about 5,730 years, which means that the present amount in your bones will reduce to 0 never. Because it never actually reduces to 0. It just keeps getting smaller and smaller and smaller, but it never gets to 0. A certain radioactive element has a half-life of 1 hour. If you start with a 1 gram sample of the element at noon, how much of the same element will be left at 4? So that means 1 to 2, 2 to 3, 3 to 4. That's 3 hours. So we get half, a fourth, an eighth. So an eighth of a gram is 0.125. Wait. We said it started at, has half-life, if you start with a sample of the element at noon, so that's noon to 1, 1 to 2, 2 to 3, 3 to 4. I just miscounted my hours. So instead of 1/8, it's going to be 1/16, which is this one. Okay. Atoms can transmute into completely different atoms in both of these. We know that. When a particular isotope emits an alpha particle, what new element results? The same element with decreased mass? Probably not. Maybe. One with both atomic number and atomic mass decreased by 2. That sounds good. One with atomic number decreased by 2 and atomic mass decreased by 4. No. Oh, remember, it's proton and neutron getting ejected. So the atomic number is going to be reduced by 2, but the mass number will be reduced by 4 because 4 nucleons are leaving. So that sounds like the best answer. One with atomic number increased by 2. No, not increased. So it's going to be this third one. Okay. When a particular isotope emits a beta particle, what new element results? Well, we know it's ejecting a beta particle, converts a neutron to a proton. So the atomic number is increased by 1, and the mass number is unchanged. So both the atomic number and atomic mass reduced by 1? Nope. The same element? No. One with atomic number increased by 1 and atomic mass reduced by 1? No. One with atomic mass increased by 1 and no change in atomic mass, the last one. A certain element emits 1 alpha particle, and its products then emit 2 beta particles in succession. The atomic number of the resulting element is changed by, well, an alpha particle, 2 protons leave, and then 2 beta particles convert 2 neutrons to 2 protons. So we lose 2 protons, but we gain 2 from beta emission. So that's 0 in total. Okay. Carbon-14 is a radioactive isotope of carbon that is primarily produced by cosmic radiation in the atmosphere, food we eat, Earth's interior, fallout. It's going to be atmosphere because we know those neutrons to convert it is coming from space. To determine the age of the oldest geological materials, scientists turn to the radioactivity of, what we said, carbon-14. Determine the age, to determine the age of the oldest geological. That means billions, millions of years. And I'm thinking, if it's biological materials, then it's going to be like Roman ruins or something from archaeological history. That would be carbon-14. When we're talking geological, it's got to be uranium. Okay, got that one wrong. Nuclear fission was discovered and correctly identified by humans. Well, this happened right before World War II. So that's going to be near the middle of the 20th century. Okay, the force that tends to push the atomic nucleus apart is electrical. Nuclear forces tend to hold it together. Chemical forces, they aren't really forces, so it's electrical. The greater the surface area for a given mass of uranium, the less likely a chain reaction. So if we have a ball of uranium, when there's lots of decays, the neutrons are inside the material. But if it's got lots of surface area, then the neutrons are free to leave more often. So it's less likely to have a sustained chain reaction. It's not more likely. We want a more compact amount of mass. Neither, that's not true, so it's going to be the first one. A major problem in chemically separating uranium-235 from the more abundant uranium-238 stems from the fact that both are isotopes of the same element, have nearly the same mass, have slightly different speeds, are radioactive. Probably this one. I also like the second answer, but I'm going to go with A. Okay. A nuclear fission reactor is an elegant way to heat water. That's true. Unlike a fossil fuel plant in every major way. No, it's almost the same, except a fossil fuel plant uses either oil or coal to heat water, whereas nuclear uses nuclear fission. The only way known at present for getting energy from nothing. Well, we don't get energy from nothing. Major polluter in the atmosphere. That's not true, so it's got to be this one. Plutonium is an element that fissions like uranium. That's true. Can be used in nuclear power plants. That's true. Ranks as a low cancer-producing substance. That's true. We just don't interact with it much. That's A. All of these. Among lightweight hydrogen, middleweight iron, and heavyweight uranium, which of these three elements has the least mass per nucleon? That is, which effectively has the least massive nucleons in its nucleus? Well, that's going to be iron. Iron has got to have the least amount of mass per nucleon because it's got the lowest energy. Remember, we fuse hydrogen to get closer to iron, and we fission uranium to get closer to iron. So it's got to have the lowest. Okay. When a sample of material undergoes fission, the total mass of the material after the event is less. So if it undergoes fission, it's breaking it up. The mass drops, and that's the energy released. Okay. In either a fusion event or a fission event or a fusion event, the quantity that remains unchanged is, well, we talked about this before, energy is released. The mass of the nucleons just changes slightly. The number of nucleons is the right answer. To calculate the energy release of either a fission or a fusion reaction, first find the change in mass and, well, this is Einstein's famous E equals mc squared. So we've got to multiply the mass times c squared, not divide it. We've got to multiply by the speed of light squared. That sounds right. Square it. We're not going to square it. Take the square root note. So it's this one, B. Work is required to remove a nucleon from the atomic nucleus. When this occurs, the removed nucleon, well, when it's removed from the atomic nucleus, it's going to gain some mass. If an iron nucleus were to split in two, its fission fragments would have, well, if it splits in two, the fission fragments are going to have more mass because it takes energy to break up iron. So you have more mass per nucleon. And that's it, and I'll see you guys next time.